Turing machine is a finite state machine with the ability to read and write data to a tape. Essentially, a finite state machine consists of a number of states, finite naturally. When a symbol, the character from some alphabet say, is input to the machine, it changes state in such a way that the next state depends only on the current state and the input symbol. You can represent the finite state machine in a form that makes it easier to understand and think about. All you have to do is draw a circle for every state and arrows that show which state follows for each input symbol. For example, the finite state machine in the diagram has 3 states. If the machine is in state 1, then an 8 moves it to state 2 and a B moves it to state 3. The 3-state finite state machine. A Turing machine is a finite state machine that has an unlimited supply of paper tape that it can write on and read back. There are many formulations of a Turing machine, but essentially the machine reads a symbol from the tape, which is used as an input to the finite state machine. This takes the input symbol and according to it and the current state does 3 things. 1. It prints something on the tape to move the tape right or left by 1 cell. 3. Changes to a new state. A Turing machine can also perform a special action. It can stop or halt, and surprisingly it is this behavior that attracts a great deal of attention. For example, a Turing machine is said to recognize a sequence of symbols written on the tape if it is started on the tape and halts in a special state called a final state. What is interesting about this idea is that there are sequences that a Turing machine can recognize that a finite state machine can't. For example, a finite state machine can recognize a sequence that has 3A followed by 3B, for example AABB, and so can a Turing machine. But only a Turing machine can recognize a sequence that has an arbitrary number of A followed by the same number of B. That is, a Turing machine is more powerful than a finite state machine because it can count. This at first seems very odd, but a little thought reveals it to be quite reasonable, obvious even. To discover if the number of B is the same as the number of A, you have to do something that is equivalent to counting them, or at least matching them up, and given there can be arbitrarily many input symbols even before you ever see the B, you need unlimited storage to count or match them up. The finite state machine doesn't have unlimited storage, but the Turing machine does in the form of its tape.